Welcome back. We continue our discussion on mathematical models that incorporate protease inhibitors. So this would be part two of this lecture. And so we quickly, briefly remind you that the terms that are incorporated here in the mathematical model for the inhibition of protease are terms that have to do with the production of both of um, Y, which denotes infectious virions, and the production of Z, which denotes non-infectious virions. So what we are dealing with is that basically this rate of production, which is also a constant of proportionality, right? The amount of particles of virus here are produced in proportional to the amount of infected cells. And so that constant of proportionality pi is now split between a fraction 1 minus eta and another fraction eta. And that is how the treatment reflects on this context. So let's go back to view some of the numerical solutions for different values of eta. And what we had seen before is that when there is no treatment, when eta equals 0, or with a treatment that's 0% effective, then the solutions of the system are those equivalent solutions to a stable endemic equilibrium point. Specifically, the population of non-infectious viruses decaying to 0 rather drastically. Okay, so what happens if the treatment considered is a non-trivial quantity? This is the first case we consider when that production of infectious virions is reduced by half, so from pi to half of pi, or also the production of non-infectious virions is affected in this case by the same quantity. But what we see is that that state variable z of t, which was converging to 0 very, very fast, is now taking on values that are completely non-zero. So if we increase the effectiveness in treatment, we expect to see consequences on these levels of um, established variance. Okay, so what happens if that is, say, 4/5, which is 0.8? So this corresponds to a treatment that's 80% effective. And what we observe is, maybe I go back here, the amount, in this case, for these particular values, we have a match. The amount of infectious virions are matching the amount of non-infectious virions. Well, that's also by virtue of having a production rate that's split, is identical. Uh, but now, in this scenario, we can see how the amount of non-infectious virions is outcompeting, is larger than the amount of infectious virions. So there are more particles of virus in this host circulating around. There are more particles of virus that are non-infectious. That's what you can see the level here, the plateau is a larger number. More non-infectious virions than infectious virions. Okay, and as we increase this number, the effect will be more drastic. So if now we consider that the effectiveness is 95%, then we can see a very drastic change. When we go back here within a time window from 0 to 10, there is rather sharp, steep positive slope, if you will, of both the non-infectious virions and the infectious virions and the infected cells. But now we can see that that slope is a lot still positive, but a lot smaller, and this means that um, it takes a lot longer for the amount of infectious virions to attain uh, significant levels. Before the plateau for infectious virions, that plateau was on the order of 10 to the 6. You can see that here the positive equilibrium level is on the order of 10 to the 6, while now it seems that those infectious virions are, are going to plateau quite, but at a longer time scale, they're still not at levels as they were before, and it seemed they would plateau a little over 10 to the 4, um, but not quite as high as before. So we know that this parameter, as we're considering in the model, is bounded between 0 and 1. So the largest eta can be is 1. And when eta is 1, that would be a treatment that is 100% effective. So as a last case study, we consider simulations for a value of effectiveness that is not quite eta equal 1, but is significantly larger than the previous value that we saw. And we can see you should definitely go and code up these equations and verify it. You should verify your solutions for all these different values of eta, and you should also verify what do you obtain when eta is exactly equal to 1. And what we see in this case, though, where is extremely close, I mean, this is more than 99% effectiveness, right, is that it is possible to basically perturb the system away from something that looks like an endemic equilibrium, perturb the stability of that steady state, and basically uh, force the time solutions out of the basin of attraction of an endemic equilibrium into the basin of attraction of a steady state that is free of infection. So now infected cells, infectious virions, and non-infectious virions are all headed towards converging to 0. And the population of uninfected cells seems to be converging or settling into a plateau. And of course, this is only a simulation. These are artificial values, but you can use this as an illustration of the ideas here and how is rather simple to incorporate terms that denote treatment schedules for these simple mathematical models. Thank you.